Right. So welcome to this chapter of link analysis again. So in the last lecture, we have discussed about PageRank and DivRank. Okay, and we have tried to, understand how topological structures are generally used to rank nodes. Okay, and but here in today's lecture, what we will do, we'll discuss how a pair of users, right, a pair of nodes, right, can be used, right, to measure the similarity. For example, say if I mean, PageRank and DivRank try to give a ranking of nodes, right, irrespective of any other node. But here, what we do, we fix a particular node, right, and check which are the other nodes which are similar to the given node. Okay, say here the task is say let's assume that you have 5 products: product 1, product 2, product 3, product 4, and product 5. And the question that we want to answer here, that given a particular product 1, right, say the product is 1, which are the other products which are similar to 1? Okay, say among these 4 other products, which product is most similar to 1 compared to others? Okay, so here you see that we fix a particular item and then we basically rank other items. So essentially what we do, we will measure the similarity between 1 and 2, 1 and 3, 1 and 4, 1 and 5, and then rank, right? So this is with respect to a particular item. Whereas if you look at PageRank and DivRank, that is irrespective of any query or any particular object. It basically says that given a particular network, just rank all the nodes based on something, based on PageRank or based on DivRank. But here what I'm saying is that given a network and given a particular item, rank other nodes, other items with respect to that particular item. Okay, so this is similarity between 2 objects. Okay, so so here we will discuss 2 different ranking mechanisms. One is called SimRank, okay, and other is called the PathSim or MetaPathSim. Okay, so SimRank, we will see that we will use homogeneous network, and in the next concept we will use heterogeneous network. Okay, so far we have not used any metadata information, any meta information. What do you mean by meta information? Say for example, you know the object type, or you know the relation type. Okay, we have not used those concepts so far, right? So here what we'll do, that we'll try to first understand the context of a particular item, right? A context of a user or the context of a node is basically determined by its neighbors, right? Say for example, it's a network A, B, C, D, right, E. So the context of A is defined by neighbor B, C, and D, because B, C, and D are directly connected to A. Okay, so the idea is very simple. The idea is that 2 nodes are similar if their context are similar. Okay, 2 users are similar if their friends are also similar. It's a very simple idea. This also, this also resembles with the concept of distributional similarity in NLP, where it basically says that a context, right, of a word basically indicates its meaning, right? So here also we are saying that, okay, if you want to understand the similarity between 2 items, you basically look at their context and you see how similar those 2 contexts are. Okay, so this is the idea, right? Now, how do you define context? Here we define context based on the direct neighbors. You can also define context based on multi-hop neighbors. Say neighbor 1, neighbors with I mean hop 1, hop 2, and hop 3, so on. Right. So SimRank, right, is a very simple measure very simple yet very effective measure. So the idea is that now let's consider this graph. Okay, now assume that this is a citation network where paper E cites paper C and D, paper C cites A, paper D cites B, and so on, right? So in this citation network, we can say that paper C and paper D are similar because both the papers are cited by E. Okay. Similarly, paper B and paper G, these two papers are similar because they are cited by H. Okay. In bibliographic, in scientometrics or bibliometrics, there is a concept called co-citation index. Co-citation index. Right? What is co-citation index? Co-citation index between a pair of papers is measured by the number of common papers which cite both these papers. Okay, so let's assume that this is A, this is B, right? Right. Say for example, X cites AB, Y cites A, Z cites A and B, and this another P cites P, right? So co-citation index is basically measured by the number of papers which cite both A and B. How many papers cite both A and B? 2 papers cite both A and B, right? Out of how many? Out of 4, because the maximum possibility is 4. So this is basically, neighbor of A intersection neighbor of B by neighbor of A union neighbor of B. A very simple Jaccard coefficient, right? This is called co-citation index. Similarly, the reverse index is called bibliographic coupling. Bibliographic coupling. Right? What is this? It basically says that the bibliographic coupling between two nodes, between two papers, is measured by the number of papers, by the number of common papers which are cited by both these papers. This is so in co-citation index we are considering in citation or citation, whatever. In bibliographic coupling we will consider references, right? Say for example, let's again consider A and B, and A cites X, Y, B cites X, B cite Z, right? So the bibliographic coupling is again right, out neighbor of C intersection A intersection out neighbor of B by out neighbor of A union out neighbor of B, which is in this case would be and this is mod. Okay, mod. So this would be 1, so which is X, right, by 3. This is called bibliographic coupling, right? So here you see again, in both these two cases, we are measuring the similarity of two nodes based on the other nodes, right, that these nodes are citing or cited by. SimRank is very similar, but SimRank takes into account another granularity. What SimRank says that let's say this example, okay? So SimRank says that the similarity between X and the similarity between A and B is the similarity if the similarity of the similarity of neighbors of A and neighbors of B. Okay, so let's take this example. So let's say there are two papers again, A and D. So A and D are not directly cited by any papers, or A and D are not citing other paper directly, right? So A and D, if you see, A is cited by A each, A, F, and C, but D is cited by E, right? In that case, how do you define the similarity between A and D? So the idea is the similarity between A and D is the similarity of E and C plus similarity of E and F and so on, because C and F are A's neighbors and E is D's neighbors. So the similarity of A and D is similarity of A's neighbors and D's neighbors. Okay, that's the idea. So let's formally define it. Okay, let us take some notation. Let's assume that IV is the inward neighbors, the set of inward neighbors of V. Okay, and OV is a set of outward neighbors of V. Inward neighbors means the nodes which are pointing to V, right? And OV is the nodes which are pointed by V, assuming that it's a directed network. Okay, in case of undirected network, doesn't matter, same. Okay, so now, so the SimRank of A and B is defined in this way. So if A and B are same, the same object, meaning SA comma A, then it is one maximum, because the similarity of an item with itself is maximum. If A and B doesn't have any, if A or B doesn't have any neighbor, if A or B doesn't have any neighbor, meaning A is an isolated node, for example, and B has some neighbors, or B is an isolated node, A has some neighbors, or both A and B are isolated nodes, they don't have any neighbors, right? Then the similarity is 0. It is again obvious. So these are two corner cases. Third case, when first two conditions do not satisfy, it basically says that the similarity of A and B is some constant. I will discuss this constant later. Okay, let's look at this one. What it is saying, that we take one particular neighbor of A, which is denoted by I, and we take one particular neighbor of B, which is denoted by J, right? So I goes from 1 to mod IA, and J goes from 1 to mod IB. Okay, I take one particular neighbor of A, which is I, and one neighbor J, which is one neighbor of B, which is J, and then we basically measure their similarity. Okay, and how do you measure I's? How do you measure the similarity of I and J? The similarity of I and J is again be used in this way. So case of when you measure the similarity of I and J, what do? You basically again do the same formulation, some constant summation of, right, I's neighbors and J's neighbor similarity. So you see there's a recursive formula, right? Now, if you do it in a very naive manner, this recursive formulation, now this is the way you define it. Okay, now this is the extensive way of defining things. Now I'm trying to make it little naive, little simple. Okay, so again these are two corner cases. Okay, I'm again measuring the similarity between A and B. What I'm saying is that if A and B are same, then 1. If A and B are different, then 0. Okay, and right. So now let's look at this. Now this is true when I equals to when you start with the first iteration. So iteration 0. So iteration 0, you say that okay, if A and B are same, then it is 1. If A and B are same, this is 1. Otherwise 0. Okay. Now how do you iteratively update it? So this is I equals to 0 at the initial stage, right? Now at k plus 1 stage, so page rank or sim rank of A and B at iteration k plus 1 is as follows. If A and B are same, then we have 1. If A and B are different, then you basically take the similarity of their neighbors at kth time. So k plus 1th time, the similarity of A and B is denoted by the similarity of A's neighbors and B's neighbors at time k, at iteration k. Okay, and in this way we keep on iterating things. Now let's take an example. One example is given in the book. Okay, I'll discuss an example, but after after a few minutes. So now in this particular example, in this particular formulation, we have not considered any types of neighbors or any types of objects, right? Now let's assume that you also know the types of objects. Let's assume that it's a user product bipartite network. Okay, it's a user product bipartite network. You have users, you have products, and if user has bought certain products, you can see a directed link. So far you have seen that we have not used any OV in the formulation because we assume that it's an undirected network. So in undirected network, in degree and out degree are same. Okay, now let's assume that it's a directed network. Okay, it's a directed network like this, and you have users U1, U2, U3, you have products P1, P2, P3. Okay, so in that case, if you want to measure the similarity between two users U1 and U2, how do you do that? So U1 and U2 are the similarity between U1 and U2 are measured by the similarity of their common, so not common, all the similarity of their outward neighbors, right? So in this case, you see that U1 has the outward neighbors P1, P2, U2 has its outward neighbors P1, P3, right? So you basically measure the similarity of P1, P1, P2, P2, P1, P2, P3, right? Now, in order to calculate the similarity between P1 and say P1 and P3, how do you do that? The similarity between P1 and P3 is again defined by the similarity of their inward neighbors, right? So P1's inward neighbors are what? P1's inward neighbors are U1, U2, right? And P2's P3's inward neighbors are only U2, right? So then you measure the similarity between U2, U1 and U2, U2, and U2, U2 similarity is 1, we know. So then we need to measure the similarity between U1 and U2, right? So you see the point here. So for measuring the similarity between two users, you take their outward neighbors and outward neighbor similarity. To measure the similarity between two products, you take their inward neighbors and their inward neighbor similarity. So then you may wonder, then when do we stop? It seems like we keep on depending on each other, but that's it's not very intuitive that how to stop, right? So let's take an example, then you will see that it will stop. Okay, so let's assume that here this is a bipartite, simple bipartite network, and 2 users, 4 products, right? And let's say the task is to measure the similarity between A and B, user A and user B, right? So let's define the inward neighbors and outward neighbors. The inward neighbors of A is the outward neighbors of A is K, L, and M. The outward neighbors of B is L, M, and N. Okay. The inward neighbors of K is only A. The inward neighbors of L is A and B. The inward neighbors of M is A and B, right? And the inward neighbors of N is only B. Okay. So as per the formulation, the similarity of A and B, right? Forget about the constant. Okay, let's discuss the constant very quickly. So the constant says that you have certain C, which is a constant that you can define earlier, right? And the denominator is the number of U1s out neighbors and number of U2s out neighbors. Okay, and here the denominator is number of U2s, number of P1s in neighbors and number of P2s in neighbors. Okay, because this is the maximum number of common neighbors that you can, maximum number of pairs of common neighbors that you can think of, right? So it ensures this denominator ensures that the similarity would always range between 0 to 1. The maximum value of this would be this one. Pause and ponder. Okay, think about it. Why this is the maximum number? Because this is the maximum possible pairs, right? So now let's again come back to the example. The similarity of A and B, right, is what? Is the similarity of A and B is the similarity of their pairs, their outward neighbor similarity, right? So it means the similarity of, now let's look at the outward neighbors of A, KLM, and outward neighbor of B, LMN, right? So we take all pairs, the similarity of KL, KM, KN. Then again the similarity of LM, right? LL, LM, LL, and similarity of ML, MM, and MN. Right? There are 9 possibilities. So you see here 1, 2, 3, 4, 5, 6, 7, 8, and 9 possibilities. Right? Now, if you see here carefully, S of LL, the similarity of L with itself is 1. So this is 1. We don't need to compute this further. This is also 1, right? Right? These two things are 1, right? So now let's look at how to compute this one, S of KL. So S of KL, similarity of K of L. How do you measure it? Similarity of K of L is the similarity of A, right? Because K's inward neighbor is A and L's inward neighbors are A and B. So then similarity of AA and similarity of AB, right? And look at here, the constant times similarity of AA plus similarity of AB, right? Now similarity of A is 1, right? And similarity of AB is something that you do not know, right? So this is what? This is C2 by 2 times 1 plus 1 plus this one, right? So this is C2 by 2, 1 plus S of A comma B, right? If we unfold it, C2 by 2 plus C2 S A comma B by 2, right? So this is the value of S of K of L. So I can replace this value here, right? If I replace this value, I get something which is a function of S of AB. S of AB is something that I want to determine. So what is our target? Our target is to get the values of all these items in terms of S of AB. The target is to get the values of all these items in terms of S of AB, so that finally we get an equation where the unknown is only S of AB, right? So S of KL we get how to we saw how to derive it, right? Similarly, S of KM, right? Because S of KM is the next unknown. Now S of KM is basically the similarity of what? The similarity of the K's neighbor is A and M's neighbor is AB. So S of KM is basically similarity of AA plus similarity of AB. Similarity of A is 1 and similarity of AB is basically this one, which is unknown, right? So the kind of same formulation that we'll get here also. Similarly for Kn, for S of Kn, we get something in terms of S of AB, right? Similarity of this one is 1. Similarity of LM is again something that you derive in terms of S of AB, and so on and so forth, right? So you see all the items, right, are defined in terms of S of AB. right? So if you replace all of them by the function of S of AB, what you do, and if you just do some small calculation, you will basically see that S of AB is this one, 3C1 C2 plus plus C1 by 9 minus 4 C1 C2. Now C1 C2 are constants, right? C1 corresponds to C1 is used when you measure the similarity of two users, and C2 is another constant. It is used when you measure the similarity between two products, right? These values can be same, these values can be different. This is completely user driven. User will set the values. Okay. So you can easily measure this. Now, if you assume that C1 and C2 are same and it is 0.8, for example, then you get that similarity of A and B is 0.547. Okay, now you believe that it will terminate, it will converge. Okay, so what is the aim? The aim is to write the values of these components in terms of the original similarity that we want to compute. Right. Now let's look at this constant very carefully. Okay, let's go back and check this constant. What does it mean? It says that C by mod of IA and mod of IB times, right? So I said that this is the highest value, this is the maximum value that you can obtain, because this encompasses all pairs. Let's say A has 5 neighbors and B has 6 neighbors, right? So how many pairs are possible? 5 into 6, right? So here you're taking all pairs, right? I goes from 1 to IA and J goes from 1 to IB. So you're taking all pairs of IA and IB, all pairs of items which are there in IA and IB, right? Now this C, what it does, if you think of it carefully, this C penalizes when you move from 1 hop to 2 hop to 3 hop. For example, if say this is A, okay, and this is B, this is C, okay, and D and E. Okay, so the similarity of A comma A is maximum, which is 1. Okay, similarity of A comma B, right, and similarity of A comma C, this would definitely be less than similarity of A comma A, less than similarity of A comma A. Here similarity of similarity of B comma D, similarity of B comma D, right? Similarity of B comma D is less than, because we start from A. Okay, this would definitely be less than similarity of A comma B, which is further less than similarity of A comma A. So till this part you have C. When you move from this to this, because you start calculating the similarity between A and B, you take C, right? When you calculate similarity of similarity of A and D, right, or B and D, not A and D, B and D, you have C times C square, and remember C is a constant which ranges between 0 to 1. Say C is 0.4, for example. So when you do C square, basically C square is less than C, right? So it ensures that when you move far away from the root node with respect to which you are computing the similarity, your C value deteriorates, right? And that in turn penalizes the similarity. Okay, so this constant is something, the value of C is something that is in our hand. We can make it 1 without thinking much, right? And otherwise we can also make it any value between 0 to 1. Okay. Now this is SimRank, and in the book you will see that there's another example where the derivation of SimRank is given. You can look at it. All right. So now what we will discuss is very interesting. Now this is a very new concept. So we'll discuss something called heterogeneous network. And heterogeneous network, what is heterogeneous network? We briefly discussed in the first lecture. Okay, heterogeneous network is a network where nodes can be of different types, edges can be of different types. So nodes can be of different types, or edges can be of different types, or both nodes and edges can be of different types. Right? If nodes are of different types but edges are of same types, it is called node heterogeneous network. If nodes are of same types but edges are of different types, it is called edge heterogeneous network. Okay, let's take an example. Let's assume that you have a citation network where nodes can be of different types. Okay, say nodes are papers, right? Paper 1, paper 2, and other type of node is author. Okay, author 1, A1, A2. So if paper 1 is written by author 1, there's a connection. If paper 2 is written by A2, there's a connection, right? And so on and so forth, and so on and so forth. So here nodes are heterogeneous but edges are homogeneous, because all the edges indicates write by relation, right? Or written by relation. A1 has written this paper, A2 has written this paper, therefore there is a connection. A1 has written this paper. So these edges indicate written by. Same types of edge. So this is called node heterogeneous network, right? You can also make it node. You can also make it node heterogeneous and edge heterogeneous. How? If you add an edge, if you start adding edges from between two papers as citations, right? There's a link from P1 to P2 if P1 has cited P2. So then you see that there are two types of edges. One is an undirected edge which indicates written by. Another is a directed edge which indicates cited by. Right? You can add another type of edge between two authors. Right? This indicates co-authorship. If A1 has co-authored with A2, right, then there's a link between A1 and A2. And this co-authorship relation can easily be inferred from written by relation, because if A1 has written if A1 has written P1, right, and A2 has written P1, then A1 and A2 are definitely co-authors. So you can infer these edges. Otherwise, you can directly add these edges. Okay. So you see that there are two kinds of there are three kinds of edges: written by, cited by, co-authored. Right? So edges are heterogeneous, nodes are also heterogeneous because nodes are of different types. Right? You can also add another type of node which is called venue or conference or journal, right? And you can add an edge from P1 to that conference. It basically indicates that this particular paper has published in this conference, right? And so on and so forth. You can make it complicated. You can keep adding different types of nodes here. So we have seen in this case node heterogeneous or node heterogeneous and edge heterogeneous. Now let's look at only edge heterogeneous. Okay, node homogeneous, but edges are heterogeneous. Okay, let's see. Let's consider Twitter. Okay, users: user 1, user 2, user 3, user 4. If user 1 has followed user 3, there's a directed link. Okay, so this indicates follows relation or followed by relation, right? If user 1 has retweeted if user 1 has retweeted user 4's tweet, there is again a link. Now this indicates retweets or retweeted by. Okay, so you see here, nodes are homogeneous, but edges are heterogeneous, right? So when we define a heterogeneous network, uh, it is defined by the following tuple: V, E, A, R, phi, psi, right? So this indicates the set of, what is this? Set of edges. What is A? A indicates a set of types of nodes. Okay, types of nodes means, in this case, the types of nodes are authors, papers, venues, right? So A is a set, indicates the types of nodes: author, paper. R is a set of types of links. Okay. So now you see that there are two mapping functions, right? One is phi and there is psi. Now phi is a mapping function which maps a vertex to a particular node type, vertex type, right? You see a mapping from V to A, right? Vertex set to a vertex type, and psi is a mapping which maps an edge to a edge type. Okay, right? So guys, I'm pretty sure that you can relate this structure to something that you have read earlier. Can you tell me? These kind of structures you have read somewhere in your undergrad. Where? Can you relate this? In DBMS, any concept? No? There's something called ER diagram, entity relationship diagram. I'm pretty sure you have gone through the entity relationship diagram. This is exactly entity relationship diagram. There also you had entity types, relationship types, right? Here also you have node types, edge types. Okay. Gradually, as we discuss, as we move along, we will see that it exactly is same as the entity relationship type. Therefore, when this heterogeneous network concept was invented or proposed in network science community, the database community started saying that, look, this was invented 30 years back. So don't call it as heterogeneous network, just call it as entity, kind of a ER diagram, right? But anyways, there was a debate in 2011 that this is not a new concept. This was discussed long time back. You are basically giving it a different color, different wrap altogether. But no, this is exactly same. Anyway, so in heterogeneous network, you can have different types of nodes, different types of relations, edges, and or. I mean, either homogeneous, either node heterogeneous or edge heterogeneous, or both nodes and heterogeneity. Okay. This is an example of user product bipartite network. You see that this is node heterogeneous because you have one partition constituting nodes of user type, one partition containing nodes of product type, and links basically indicate bias, whether a user has bought a particular item or not. Well, links are homogeneous, right? This is again a link. So this is link heterogeneous network. Nodes are all persons, right? Individuals, and links are of different types of friends, whether they are family friend, whether they are colleague, whether they are school friend, and so on and so forth. Okay, so this is link heterogeneous, and this was node heterogeneous. Okay. Citation network, as I mentioned, this is a case of both link heterogeneous and node heterogeneous, because nodes can be of different types, links can be of different types. Okay. Now we define something called a network schema. Okay. Now you start feeling that this is same as entity relationship diagram. Okay. We define something called network schema. Okay. What is network schema? A network schema is defined very simple. A network schema is defined by the set of node types A and the set of edge types R. Okay, this is a network schema. So now what I'm saying is that, you know, we now we start defining the relations between node types and relations between edge types. I'm not talking about the relations between nodes. I'm talking about the relations between node types. Now, what's the difference between nodes and node types? Node types are authors, venues, conferences. These are node types in citation network. What are the nodes? Nodes are, you know, author Smith, Dr. Smith, paper, a particular node, a particular paper node is, say, a particular paper titled support vector machine, right? A venue node is a particular venue, say SIG-KDD. Okay, so these are the different instances of node types. Okay, similarly, we have instances of edge types, right? If there is a link, from author Michael Jordan to author, you know, author Yuri Leskovic, right? If there's a link between these two authors, right, which indicates co-authorship link, right? So the link type is co-authorship, but the instance is a link between these two authors. So what I'm trying to say is that given a particular link type, there can be multiple instances of that link type. Similarly, given a particular node type, there are multiple instances of that node type, right? You see my point? So network schema indicates the relations between node types, not between nodes. Okay, so let's assume this network schema. It basically says that an author can be connected to a paper by a link write. Any author can be connected to any paper by a link write. It means that author has written this paper. A venue can be connected to a paper by a link publish. That means this venue published this paper. A paper is connected to a term or a keyword via the link contents. That means the paper contains this term, right? So the schema basically says that you can't arbitrarily connect any node pairs, right? You can connect, I mean, you can't connect an author and a venue, and an author node and a venue node via write, via the edge write. This is not possible. This is not permissible. This is not permitted, right? What is permitted is that if you really want to connect two nodes through the link write, the source node would be an author and the destination node would be a paper. It also says that you can't connect a node venue with a node term by the link relation publish. You are only allowed to connect a venue node to a paper node via the relation publish, right? So this network schema in some ways, you know, allows you or restricts you to make connections in an arbitrary manner. You see my point? So network schema is basically a relation between different types of nodes, different node types. Okay, I'm not talking about any instances. I'm just talking about types. Okay. Similarly, here this is a network schema of a movie network, right? The director directs a movie, actor acts in a movie, user rates a movie, and so on and so forth. Right. So I hope you understand the difference between network schema and a network. Okay. Now whatever I'm going to discuss, all would be based on network schema. Just assume that you have different node types, and node types are links by different relation types. Okay. Now I define a very novel concept called metapath. What is metapath? Metapath is a path in the network schema graph which connects two different node types via certain relations. Okay, so a metapath is a path of length L defined by a composite relation over L hops. Okay, and the composite relations look like this: R1, R1, then concatenated by R2, then R3 dot 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 RL, and it connects two types of it basically connects L plus one types of nodes. Okay, let me give an example. So you see here, this is a meta path. It basically says that there's a meta path from an author to another author, okay, of length 2. This L is 2 in this case. So and the meta path consists of paths edges like author to paper, paper to author. So if you see here, so author, right, writes paper written by author. Okay, this is a meta path of length L, right? You see there are two different edges, two different edge types. One is written and is written by, right? By the way, written and written by are same. One is just the reverse of other. Written by is just the reverse of written. Okay, written inverse. So you see that this is a meta path which connects meta nodes, okay, or node types via different edge types. Clear? Similarly, this is another meta path. Author, paper, venue, paper, author, author to venue to author to paper to venue to paper to author. Now, a very interesting concept here is that a metapath cannot be of any random type. Say for example, this APA or APVPA. Let's look at the network schema, right? APA and APVPA. Let's try to understand whether these two metapaths are at all valid metapaths or not, right? So APA. So APA is possible because A is written, A has written this paper, and this paper is so if there's a link from A to P via the edge type right, there can be an opposite link from P to A via the edge type right inverse, which is written by. This is possible. So APA is a valid metapath. Now look at APVPA, A to P to V, right? Because if this exists, the reverse also exists, right? If this is published by. So A P V P A, this is possible, right? But what is not possible? A T P, not possible, right? So if you are given a schema, you can be able to enumerate all possible metapaths, right, between two types of between nodes of same types, right? For example, between two authors, this can be one path, APA. Between two authors, there can be another path, APVPA. Between two authors, there can be another path, APTPA, right? Between two authors, there can be another path, APVPTPA, right? But these paths are of different lengths, right? So when I say a particular metapath, I first fix the length. I say that, okay, let's fix the length equals to 5. Okay, so you enumerate, you basically extract all metapaths of length less than 5 or less than equals to 5. So when I say less than equals to 5, then APA is possible, APVPA is possible, right? APTPA is possible, but APVPTPA is not possible. Okay. Right. Okay, so these are the two metapaths, two types of metapaths between two authors, right? This is a metapath between an author and a venue, right? And so on and so forth. Why this is called metapath? Why this is not a path? This is a metapath because this path is defined within the vertex type or node type. This path is not defined by the actual nodes. These paths are defined by node types. Therefore, this is called metapath. Node types are nothing but meta nodes, right? Edge types are nothing but meta edges. So therefore, this is called metapath. Okay. So try to understand. We have now moved from actual network to a network schema, and we are defining everything with respect to the network schema. And then whatever we define here, then we map everything to the actual network later. How? So let's assume that if I say that, okay, tell me how many instances of metapath APA type exist in the graph. What I'm saying is that how many instances of this metapath type APA exist in the graph. So you basically start looking at, okay, there's a citation network, there's a publication network, right? And then you see that, okay, Mr. X has published a paper at venue, Mr. X has published a paper P, and this paper P has also written by Mr. Y. So this is one instance. This is one instance of type APA. There's another instance. If Mr. A has written a paper Z, and Z has also written by Mr. P, right? So this is another instance of APA. So you would basically find out all instances, all possible instances of type APA from the original graph. When we fix the metapath, you can look at, you can easily search for all instances of that type, and that is the target. Okay. So now we define the similarity, because ultimately our aim is to define the similarities between a pair of objects, a pair of vertices. Okay. So let's define now some simple quantities. The first quantity is path count. Okay. The similarity between two nodes. Now here these are nodes, not node types. Okay. This is a two node, Mr. X and Mr. Y. The similarity of X and Y is simply the path count. What do you mean by path count? Path count is the number of paths between X and Y of type PL. PL is a particular type of metapath. So let's fix that the metapath is APA, for example. Okay. So the similarity between Mr. X and Mr. Y is the number of paths, number of actual paths, path instances that are of type APA between X and Y. Right? Author, paper, and author, right? Say between X and Y, X has written paper P, paper P1, paper P2, paper P3, paper P4, paper P5, right? These are the papers that are written by X, right? And assume that P1 and P2 are two papers which are co-authored by Y, right? So the paths, number of paths of type APA between X and Y would be 1 and 2, right? So higher the number of paths, higher the similarity. Higher the number of collaborations, higher the similarity. Simple idea. Second similarity is random walk. What it says? It says that if you start a random walk from node X, let's fix a particular metapath PL, and let's assume that the metapath is APA, right? You start a random walk from X. What is the probability that you end up reaching Y via the metapath APA? So you are here, right? You see that, right? Say there can be another connection like this or something like this, right? This is P, this is V, or something like this, right? So what is the probability that you start from here and you can follow any edge, right? But what is the probability that you follow the path APA and reach out to Y, right? So higher the probability, higher the hide the similarity. Okay, this is a random walk. The third approach is something called pairwise random walk. What is pairwise random walk? It is basically saying that, okay, let's assume that there are two random walkers, one starting from X, other starting from Y, right? What is the probability that this random walker, both the random walkers, meet at an intermediate node which is Z? So one random walker starts from X, other random walker starts from Y. What's the probability that they would meet at Z, right? Given the condition that random walker X can only follow the metapath type P1 and random walker from Y can only follow metapath of type P2. There can be other metapaths, but we have to first fix the types of metapaths, right? So what is the probability that X, the random walker starting from X, follows a particular metapath P1 and reaches Z, and another worker starts from Y, follows path P2, right? Not exactly P2 inverse, I'm telling you why, right? So another random walker starting from Y, right, follows certain metapaths and reaches Z, right? So basically the idea is, what is the probability that a pair of random walkers starting from X and Y follow a particular metapath P1, P2 and meet each other? So from Z to Y, we basically follow metapath P2. From X to Y, we follow X to Z, we follow metapath P1. So from Z to Y, following metapath P2 is same as following metapath P2 inverse from Y to Z, right? So what I'm saying is that we basically formulate the problem in this way. What is the probability that given a particular midpoint Z, a random walker starts from X following a metapath P1, and again this is a kind of independent random walk. Okay, another random walker starts from Y following P2 inverse metapath and meets Z. What is the probability? This is another way of measuring this. Okay, so the problem in all these counts, and these are very simple measures, very simple measures. The problem, and they also suffer from many problems, many limitations. For example, if you use simple path count, right, or random walk, the one that I mentioned, so these kind of measures always favor nodes with high degree. If you use pairwise random walk, it always favors those nodes which have skewed scatterness in terms of inlinks and outlinks. Meaning, it would favor those cases where a node has, say, since we are talking about two different pairs, we're talking about a pair of nodes, it would favor those cases where one node has very high degree, very high in degree, and other nodes has very low out degree. Sorry, if one node has very high in degree and other node has very high out degree, right? It prefers those cases, right? Whereas the PathSim metric that we are going to discuss now, this metric basically overcomes these limitations, right, in a very systematic manner. The idea of PathSim is very simple. The idea is that, this is the idea. So PathSim between X and Y. Okay, so what you do here, you basically do something called a round trip metapath, right? What is a round trip metapath? Let's say there are two nodes X and Y, right? You start from X following certain metapath, right? You reaches Y, you basically reach Y, and then you against follow certain metapath, you reach X. So this is called round trip metapath. In start node and end node is same. Okay, so it basically is saying that out of how many round trip metapaths, out of how many round trip metapaths starting from X and starting from Y. So there are two independent round trip metapaths. X has its own round trip metapath. X can have a round trip metapath from X to X via Y. X can have another round trip metapath through X to Z to X. Another metapath, round trip metapath from X to P to X. Similarly, Y also can have another round trip metapath via A, via B, via C. Right? So it is saying that out of how many round trip metapaths of X and Y, right? Out of how many round trip metapaths, out of all the round trip metapaths of X and Y, how many of them connect X and Y? So X has round trip metapaths via Y, via A, via B, via C. Y also have round trip metapaths via X, via Y, via Z, via P, via Q. How many of them? How many of these things actually go through X and Y? So you see here, this is a round trip metapath for X. This is a round trip metapath of Y. Okay. So let me again give an example. Okay. I'll give a solid example later, but a very quick example. So this is X, Y, right? Z, A, B, C, D. Okay. And let's assume this kind of connection. Okay. How many round trip metapaths are there for X? You see from here, right? From here to here to here to here. This is one round trip metapath, right? Similarly, let's assume that you have something here, right? Right. So this is again round trip metapath, right? By the way, so in this particular case, we fix the length of the metapath as well. It is not that we take any arbitrary length, right? Say we are only allowed to take metapath of length 4, for example, right? So here you also see for Y, there's a round trip metapath. So let's say there's a connection like this to this to this to this. Okay, now this round trip metapath does not consider X, right? So this kind of metapaths, round trip metapaths, will contribute here, but not here. So this says that the round trip metapaths of X, round trip metapaths of Y, and how many of them connect X and Y together? Y2, I'll come to that. Okay. So the beauty about this metapath, this PathSim, is that it is symmetric. It is normalized. So the ranges always it ranges between 0 to 1, and the maximum range is 1. Maximum value is 1, self-maximized, meaning that the similarity between X, X is 1, the maximum. Okay, these are the important properties that we should always have in a metric, similarity metric. Let's take an example. Okay, things will be clear. Let's take this example. So let's assume that we are only considering this metapath, author, venue, author, AVA. Okay. Now this is a statistics. You see, these are the authors: Mike, Jim, Mary, Bob, Anne, right? And these are the venues: Sigmod, VLDB, ICD, SIGKDD. These are the venues. And what does this number indicate? Mike has published 2 papers in Sigmod, one paper in VLDB, 0 paper in ICD, 0 paper in KDD. So these are number of papers. Okay. So if I say that now we have already fixed the metapath type AVA, right? If I say that what is the count of round trip metapath of Mike, round trip metapath of Mike of type AVA, what is the type of what is the count of round trip, what is the count of paths of type AVA for Mike round trip? Now let's look at only Mike, right? Say this is Mike, Jim, right? And this is Mod, Sigmod, VLDB, ICD, and KDD, right? And let's look at only Mike. So Mike has published 2 papers in mod, right? Kind of 2 parallel edges. Let's assume that 2 papers mean two edges, right? 1 paper in VLDB, right? And 0 paper in ICD, 0 paper in KDD. So how many round trip? So this is actually a round trip metapath, right? AVA, right? But here both these endpoints should be Mike. That's why it's a round trip. How many such round trip paths, round trip metapaths are there? Think about it. Any idea? How many such paths exist? Dekho. So this is path 1, this is path 2, this is path 3. This is edge 1, edge 2, edge 3. So from Mike through this edge, again coming back through this edge, or this, or this. Is this clear? Similarly, this and this. So what I'm trying to say is that so let's again unfold it. Okay, so this is Mike. Okay, and this is mod, right? Sigmod. He has published this paper, say paper 1, okay, and paper 2, and in VLDB, paper 3. Okay. So now let's look at the number of round trip metapaths of type AVA. Round trip number of paths of type AVA which are round trip. Okay. So one is Mike, paper P1, Sigmod, P1 inverse, Mike. One is, so basically this, you go through this and you come back through this. One is Mike, paper P1, sorry, paper P2, mod, P2 inverse, Mike, go through this, come back through this, right? You have Mike, paper P1, mod, you are going through this, or coming through P2, right? P2, Mike, or Mike, P2, mod, P1, Mike. Now it is clear. So how many such paths exist of type AVA? So all these paths are of type AVA, and all these paths are round trip paths, right? So how many such paths exist between Mike and mod? 4, right? What about this one? What about Mike and VLDB? So Mike and VLDB, Mike, P3, VLDB, P3 inverse, Mike. That's all. There's only one path. So how many round trip paths exist between any venues and Mike? Here 4, here 1. So 4 plus 1. And how did we get this 4? This is basically 2 into 2, right? Now you can easily do the math. For Mike, this is 2 into 2 plus 1 into 1. For Jim, this is 50 into 50, 20 into 20. And you know why. For Mary, this is 2 into 2 and 1 into 1, and so on and so forth. This is the number of round trip paths, which is the denominator of the SimRank, which is the denominator of the PathSim values, right? Now let's look at the numerator. Right now, if you look at the numerator, Think about it. Let's look at Mike and Jim. Okay. So Mike has published, now this is, sorry, this is VLDB. Okay. And this is, sorry, this is mod. This is VLDB. You have ICD, KDD. ICD and KDD. Right. So Mike has published 2 papers in VLDB, 1 paper in 2 papers in mod, Sigmod, 1 paper in VLDB. Jim has published 50 papers in mod, 20 papers in VLDB, 50 papers in mod, 20 papers in VLDB, right? That's all. So how many metapaths exist of type AVA from between Mike and Jim? So when you fix VLDB, how many metapaths exist? Tell me, between Mike and Jim.
2 into 50.
2 into 50, right? Between Mike and Jim through VLDB.
1 into 20.
1 into 20. 1 into 20. Very good, right? That's all. So between Mike and Jim, you have 2 into 50 plus 1 into 20 plus 0 into 0 plus 0 into 0 for these values. So this is 1 to 20, right? Now, if you measure the similarity, PathSim, similarity between Mike and Jim, the value would be 120 by 5 plus 2900 into 2 in the numerator. Why in the numerator this is 2? Why in the numerator this is 2? Any idea why in the numerator this is 2? Because in the denominator, we are double counting certain nodes, certain metapaths. We are double counting certain metapaths. Right? Think about it. So that's why the maximum value of the numerator would be this by 2. We wanted to make it normalized so that the range is between the range falls between 0 to 1. Okay. So now I measured the similarity between Mike and Jim, which is this one. Mike and Mary, say this one. Mike and Bob 1. Mike and Anne, this is 0. Okay. So I say that Bob is similar to Mike in terms of publications. Now let's look at the intuition. Let's look at whether this also goes with our intuition. So Mike and Bob, you see the pattern 2 2 the conference mod, 1 1 in conference VLDB, 0 0 ICD, 0 0 KDD. The pattern is same. But if you use, say, other similarity measures, right, you will see that Jim will be said as more similar to Mike, not Bob. Why? Because of the sheer number. So 50 means it has 50 edges, very high degree, right? So PathSim normalizes. Now look at this example, right? Now look at this one. So if I want to, now this is the example that I've shown. If you look at other similarity measures like PageRank, this is personalized PageRank, SimRank, random walk, personalized random walk, right? And PathSim. You see that with respect to PageRank, Jim is considered as the highest, as the most similar author of Mike, which is not correct. Similarly, in case of SimRank, if you take SimRank, both Jim and Bob are considered as the similar most similar neighbors, most similar authors of Mike, which is also not correct. If you take PathSim only says that Bob is the most similar most similar author of Mike. Okay. In the book, a concrete example is given. you please go through the book, go through the example. If you are still confused with the ideas of PathSim, this is the paper that you should read. Okay, this is the famous paper by this Philip Hughes group. So you can read this paper, you get this thing clear. Okay, thank you very much.